The nerve impulse, the definition or a description of what the nerve impulse is this is how neurons communicate with each other. This is how they tell each other to do stuff. And the official definition of a nerve impulse is the movement of action potentials
I know it's in the notes, but you tell us again what action potential is.
Yeah, I'll explain it when we draw it. So it's the movement of action potentials along a nerve fiber. So we're going to start off by drawing a neuron in a state known as the resting state. So I'm going to use a red pen just to label like what phase we're in right now. So right now when you have a neuron that's resting, this is also known as the polarized state, aka the resting state. And for those of you who took chem and absolutely loved it, what does the word polar mean? Poles, positive and negatives, North Pole, South Pole. Example of something with polarity in real life. Magnets and
Charge. The earth.
Earth and like batteries. Okay? Yeah, positive one side, negative one side. Okay? So that means a neuron is the same way. It has positive on one side, negative on the other side. Okay? That means in your body, because you are able to have neurons communicate with each other, these neurons are using electricity as a form of energy. Right? So that means you have electricity flowing through you right now. And that's why, have you guys seen cartoons or movies where someone gets like death by an electric chair? And they put on the electric chair cap and they turn it on, and then what does their body do? It like shakes and it's like all over the place. It's because the electricity is what charges or what causes neurons to communicate. So all the neurons are like firing and then everything's going crazy because everything is getting stimulated to do like random things. So that's why that happens.
What about when you get struck by lightning? How come you don't die?
Well, because your body is able to use some of that electricity, but if it's strong enough, you can. Some people do die. It just depends on the scenario, I think. So if you were to measure how much electricity something has, the unit of measurement is called a volt. You guys have heard of that, right? 9-volt batteries, 40 volt or watts for light bulbs. So if you were to measure a resting neuron, your voltage would be approximately negative 70 millivolts. So that means we have really, 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 really small amounts of electricity going on. Very tiny amounts of electricity. And using my black pen or pencil, I'm going to draw a resting state or polarized neuron. So first I have to draw those little things. What am I drawing? Dendrites.
How do you guys know that?
In the center of the dendrite, I'll have a nucleus. Good. And then we're going to have the body taper off. And this tapering off is called the axon hillock. Can you say axon hillock? Okay, so that's this little piece that's kind of like pinching off. And the axon hillock is going to extend, and this is called your axon. We're going to draw it like really fat so we can draw inside. At the ends of your axon, you have Uh-oh. You have roots? What are these little hairy things hanging off the ends of the axons? Axon terminal. Have you guys heard of the word terminal before? Airport terminal. The airport terminal, let's say you're at terminal B or whatever, the terminal means it's the very end of the airport. Okay? So axon terminal would be the very end of your axon.
So axon terminals.
There's multiple terminals, yeah. Okay. So usually on the outside of your cell here, you have an environment that is super sodium concentrated. Lots of sodium hanging out. And on the inside of your neuron, you don't have too much sodium. Instead, you have potassium.
Potassium like in crumbs.
Huh?
How does the potassium in there? It's just a gas.
It is an ion. It's like a little molecule. It's an atom. So a neuron is a cell, and a cell has a cell membrane. Okay, kind of like muscle. Remember how muscle had a cell membrane? What was the muscle cell membrane called? Sarcolemma. For a neuron, it's called cell membrane. Okay. And notice on the inside of the cell membrane, we have potassium. On the outside, we have sodium. So on the outside versus the inside, which side is more positive? Outside. Oscar, how do you know that? Well, to tell if something's more positive or not, you just got to count up which side has more positives. The outside. So the outside is more positive.
How do you know that has more?
Huh?
How do you know it has more positives?
So you just count out the pluses. So on the outside we have 1, 2, 3,
You
4.
made of that. What if
Yeah.
it's like,
Well, this is what's known as a polarized state. During polarized state, you have a more positive outside than an inside. That's just the definition of polarized, right? So on the inside, you have less positives, but we're not going to write inside as less positive. We're actually going to call the inside more negative. Okay. And then, of course, a stimulus is going to occur that's going to cause a change in the sodium and potassium. So, for example, a stimulus could be something like the weather changes, or someone stabs you, or you get really hungry, something along those lines, okay? And we'll talk about those stimuli after our stretch break. So a stimulus will occur. Let's say no one stabs you today, but maybe a spider sits on your knee in the exact spot you have a hole in your pants on your knee, and a spider lands on your knee, okay? So that will act as a stimulus, and it will cause an event called depolarization, so I'm going to write that in red. So a stimulus occurs and causes depolarization. So we're basically changing the polarity of the cell. And depolarization is caused by a stimulus, such as a spider sitting on you. A nice spider.
No spider's nice.
All spiders are nice. And it's going to change the polarity of the cell, meaning our voltage will no longer remain the same. It will actually cause it to jump to about positive 30 to 40 millivolts. And so what that's going to look like for our neuron, so let's go ahead and redraw the neuron. Exactly the same as the first one you drew, of course. Not really. Looks exactly the same. During depolarization, in the cell membrane, you have channels, so little openings. These little channels will open during certain times, but not others. So, for example, you could physically cause a channel to open. Okay, so if you have a channel here and something were to apply enough pressure, for example, a really fat spider lands on your knee, then it'll cause a change in the shape of your skin, which will trigger the channel to open up. And if the channel will open, then the sodium will actually enter into the cell. And if enough sodium comes into that first channel, it'll actually cause a channel a little farther down to open as well. If this sodium channel opens too, then we're going to have another sodium enter into the cell. And we're going to have enough sodium here. The next channel will open and more sodium will come in. And then the next channel will open and even more sodium comes in. So it just keeps adding on. It's like a cascade effect or a domino effect. Okay? So as more and more sodium comes in, remember you still have potassium in here. So the potassium are just like, whoa, getting a little crowded. A little claustrophobic in here. So all your sodium is flowing in. Yeah.
So, is that like in the video when they would go down and pop back up?
Yeah, so in the video what you saw was like a little flash of light go from one end to the other end. This is essentially the flash of light, and then when they zoomed in on what was happening during that flash of light, you saw those little pluses like going in and then going out. So this is the going in part. Taylor?
Never mind, I
Okay.
can't do that question.
So now if we analyze the outside of the cell versus the inside, which side is more positive now? Inside. So we're overcrowding the potassium by adding all this sodium in, and it does happen in a chain effect, moves down the axon, like in the video. That's what I was trying to show. And then what's going to happen next is that since the potassium is starting to feel a little bit crowded, the channels, there are potassium channels now that will let potassium leave the cell. And that's a process called repolarization. So I'm going to use my red pen. Repolarization. And this is the process of potassium leaving. And since potassium is leaving, the inside of the cell will slightly, the voltage will go down a little bit, go down, 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 down. And it's trying to come back to the original of -70. But sometimes what it does is too much potassium leaves and you end up at about -75 millivolts. So how does that look in the neuron itself? Let's go ahead and redraw your beautiful neuron. Oh my gosh. Axon hillock, axon, synaptic terminals, and then so this time you had a whole bunch of those sodiums still in there. But this time what's going to happen is you had a potassium, and during repolarization, potassium leaves. And this would be in the video when you saw the plus signs, like moving back out of the cell. So the potassium is going to exit in a cascade effect. And this is called repolarization. So you're trying to come back to the original state. And then if you take a look at the outside versus the inside now, Notice the outside, is it more positive or negative? Slightly more positive because you're bringing it back to that original polarization that it had. And the inside is slightly more negative. But obviously, this is not how it originally looked, right? Originally, there was potassium inside, not outside. So Kiara mentioned sodium-potassium pumps. Where did you learn that? In bio. So if you learn sodium-potassium pumps in bio, this is where they would play a part. If you want to go back to the original state, you would have to pay some ATP to return sodium and potassium to original. Anyways, so as you get that movement or that change of polarity along, that's what's known as electricity. So every time you have a switch between positive and negative like that, that's called an action potential. Okay? So you have a switch between positive and negative here, and then it moves down here, and then it moves down here, and then action and potential continues to move along until you hit the very end at the synaptic knob. So we're going to zoom in on the synaptic knob. And the synaptic knob should look familiar.
I thought those were axon terminals.
Yeah, so the string things at the ends are the axon terminal, but the very end tip, the last piece, is called the synaptic knob. This is synaptic knob. What's inside of the synaptic knob? Neurotransmitters, and they're in little packages called vesicles. So what's going to happen is when that action potential hits the very end synaptic knob, the vesicles will release the neurotransmitters. And where will those neurotransmitters go? The synaptic cleft.
What is synaptic?
Just an empty space
Between what?
between a synaptic knob and what? What could be here? According to the last unit, what could be here? It could be muscle. It could be a gland. So this is essentially any effector. Or it could be another neuron.
What would be the purpose of the neuron?
What would be the purpose of what?
Of putting that into the neuron?
What would happen to the neuron if it got neurotransmitters? It would do the exact same thing all across the next cell. What's the point? It keeps going until it hits an effector. To get your body to respond in order to maintain homeostasis. All right. Thanks, guys. I'll see you on Monday. Have a great weekend.